Hello everybody, and welcome to my talk. My name is Knoche, and today I will be talking about continuous API evolution in heterogeneous enterprise software systems. The talk will be structured as follows. I will start with a short motivation, then I will give an overview of our approach, and I will conclude the talk with an outlook on future work. So why is continuous API evolution important? Well, to put it in 2 words, independent deployability. We observe that many companies are switching from a traditional lockstep deployment towards independent deployments of their applications. One of these companies is a German insurance company that serves as a case study for this research. With lockstep deployment, API evolution is actually quite simple. As a provider, we know that all client applications will upgrade at the same time as we do, so every client application only needs to be compatible with one provider version. With independent deployment, however, things become more complicated. As a provider, we no longer have any guarantee that our client applications will upgrade anytime soon, so we must evolve in a way that doesn't break them. A common approach to this is API versioning. However, versioning requires manual effort by the developer, which can be error-prone and tedious, especially in large applications. A particular challenge from our case study is that some of these applications are written in COBOL, which adds further constraints. Let us now take a look at our approach to API evolution. The first major element of our approach is an API definition history on the provider side. Each of the revisions in this history is connected to its predecessor. To further illustrate this, let's take a look at a concrete example. Assume we have a customer type with 4 fields: a first name, a last name, a gender modeled as an int, and an address. As part of our evolution, we create a new revision and perform 3 changes. First, we introduce a string field, date of birth. Then, we introduce secondary addresses and rename the address field to primary address. And we change the type of the gender field from int to an enum. As you can see, there are 2 syntactic constructs that help us. First, the replaces clause denotes that the primary address field used to be the address field in the previous revision. The as clause is used to assign a particular internal name. We will see in a minute why this is necessary. The type change itself is expressed by having a field of the same name as in the previous revision, but with a different type. The API definition history contains the entire evolution history of the provider's API. However, the provider is not required to support every revision for an indefinite amount of time. Instead, it selects a subset of these revisions, the so-called supported revisions set. From this supported revisions set, we derive an internal representation, which essentially represents the union of all these revisions. To further illustrate this, let's have a look at the internal representation of our customer example. The provider internal representation of the customer types looks like this. The first name and last name fields are mandatory in all revisions and therefore just appear as string fields. The old gender field becomes optional because newer clients will no longer supply it as an input parameter. It is, however, still mandatory as an output parameter, as older clients will still require it. The same, but the other way around, applies to the date of birth field. The address field is also mandatory in all revisions, but appears under its latest name, that is, under the name primary address. The secondary addresses field is a list field and therefore implicitly optional. The new gender field is also optional. However, note that it appears under a different name because otherwise we would have a name clash with the old gender field. Therefore, we needed to supply a different internal name in the API definition in the previous example. Constructing the provider internal representation this way guarantees us that all fields and all types from the supported revision set can be mapped to this internal representation. Let us now take a look at the consumer side. In our approach, consumers need API definitions as well. However, these definitions do not have a history. Instead, they refer to a particular revision of the provider's history on which they are based. Let us recall the provider API definition from our previous example. A consumer API definition based on this revision might look like this. Note three things. First, not all fields from the provider definition need to appear in the consumer definition, that is, the consumer may select only the fields it requires. Second, the fields appear in a different order than in the provider definition, which will be important for our COBOL example later on. Third, the consumer may also assign internal names. This way, a consumer may protect itself from name changes trickling into its code. Consumer API definitions and provider API definitions interact in the following way. When initiating an interaction with a provider, the consumer encodes its input data according to its own definition and sends this definition or reference to it along with the data. The provider proceeds to look up the appropriate revision from its local revision history and matches the fields based on their public names. This is a process very similar to the dynamic schema matching of Apache Avro. The provider then proceeds to decode the data based on this mapping and represent it in its own internal representation. This is guaranteed to work due to the construction of the internal representation. When the result is to be returned to the consumer, this process is performed the other way around. This way, we guarantee that the consumer receives the data exactly as it is defined in the consumer's API definition. That is, it gets the response exactly in the format that it expects it to. The fact that responses are returned precisely in the format required by the clients is particularly important for COBOL clients. For those of you not familiar with COBOL, in COBOL all fields have static sizes and programs operate on static memory offsets, so even a small change to the layout can break compatibility. To support COBOL, we added a few extensions to our approach. First, all type occurrences in COBOL must have explicit lengths, such as string of length 30. And we consider string of length 30 and string of length 40, for instance, to be different types. This may sound a bit strict, but it makes type conversions much easier. With this rule in place, we can perform a mapping exactly as before, for instance, like this. And to convert from one format to the other, we only have to move memory from one offset to another. When we designed our approach, there were 4 goals that we had in mind and that we used to evaluate the overall feasibility of the approach. These goals were: it should be easy to use for developers and should have as little impact as possible on their everyday work. It should support H technology platforms, and the runtime overhead of the approach should be acceptable. In order to evaluate the first 2 goals, we performed a survey among case study developers, and for the last 2 goals we created a proof of concept implementation and ran some performance experiments. The results from these experiments can be summarized as follows. The approach is considered usable in practice by the developers, but they were concerned about the resulting programming model for the provider due to the potentially large number of optional fields. As for runtime performance, it is not really an issue for remote invocations, as we are serializing anyway, and the conversions can be efficiently integrated into the serialization. However, for in-process settings, where parameters may be passed by reference, the additional overhead can indeed be considerable. These results encourage us to consider the following items for future work. First of all, we'd like to extend our prototype and further evaluate our approach, with a particular focus on the resulting programming model and appropriate tooling. Further opportunities for research include a more formal treatment of the underlying evolution semantics and to explore opportunities for integrating these concepts into existing standards such as OpenAPI. This concludes my talk. Thank you for watching.